there. Get ready for a deep dive into some serially cool physics. You've been researching magnets, but we're not talking about the ones holding your kids' artwork to the fridge. We're going way deeper into the world of quantum magnets.
Yeah, and when we get down to that level, things get really wild, especially when we're talking about staggered magnetization.
Okay, staggered magnetization. I'm not going to lie, that sounds a little intimidating. Can you break that down for me?
Absolutely. Imagine a checkerboard, right? Each square has to be the opposite color of its neighbors. Well, in materials with staggered magnetization, the electrons' spins, those tiny magnetic moments they have, well, they want to do something similar. Instead of all lining up like a regular magnet, they want to be opposite their neighbors.
So it's like a constant magnetic battle at the atomic level.
Exactly. And all that disagreement, all that back and forth, it creates this staggered pattern across the whole material. Hence the name, staggered magnetization.
That makes sense. But how do you even measure something like that? We're talking about the quantum world here. It's not like you can just look and see which way these electrons are spinning.
You're telling me. Observing those spins directly is a huge challenge. And that's where the research you sent me comes in. A 1994 paper by Heisenberg and Tomlinson. They tackled this very problem. They developed a pretty ingenious computational method called the plaquette expansion to calculate staggered magnetization.
Plaquette expansion. So they basically found a new way to look at this microscopic magnetic dance.
You got it. Think of a plaquette as a small group of those electrons. By studying how those clusters interact, the researchers could extrapolate information about the magnetization of the entire material.
That's really clever, but why go through all that? Why is understanding staggered magnetization so important?
Well, that's the really exciting part. When we can understand how materials behave at their most basic level, especially their magnetic properties, it opens doors to developing some incredible new technologies. We're talking things like high-temperature superconductivity.
Now you're speaking my language. High-temperature superconductivity, that's like the holy grail. Electricity with zero resistance. But how does that connect back to these tiny electrons and their opposing spins?
It all comes down to understanding how electrons behave, how they interact with each other. See, in those materials that exhibit high-temperature superconductivity, electrons pair up and move through the material without any energy loss. And guess what plays a huge role in whether or not a material can even do that?
I'm on the edge of my seat.
The way those electron spins interact.
Whoa. So we're talking about invisible magnets inside materials that could unlock some really groundbreaking technology. That's mind-blowing.
It is. And that research you shared, that was a huge step towards understanding these complex magnetic interactions.
Okay, you've got me hooked. Let's get to the good stuff. What did the researchers actually find? Did this whole plaquette expansion thing work?
It did. They used their method to calculate the staggered magnetization and got a value of 0.71. Now, I know that might not seem like much, but
in the world of quantum physics, I'm guessing that number speaks volumes, right? So what's 0.71 telling us about this staggered magnetization?
you're right, it's all about context. To understand the significance of 0.71, we need to compare it to what other research has found. And this is where it gets interesting. Other techniques used to study this, things like Monte Carlo simulations, spin wave theory, they predicted a staggered magnetization of around 0.62 plus or minus 0.04.
Hold on, 0.71 versus somewhere between 0.58 and 0.66. That's pretty close. It's like this new method coming in from left field is confirming what others have found.
Precisely. That's what makes it so exciting. This new method, calculating things totally differently, lines up with previous findings. It gives us even more confidence in what we know about these materials. It really strengthens the evidence that they exhibit long-range antiferromagnetic order.
Okay, time for a quick definition break. What does long-range antiferromagnetic order even mean?
It means this checkerboard pattern of opposing spins. It's not random. It's not just happening at a tiny scale. This pattern persists throughout the entire material. It's like there's a hidden magnetic order.
So even though these tiny electron magnets are always pushing back against each other, there's still this underlying structure, this beautiful pattern that appears across the entire material. That's amazing.
Absolutely. It's a perfect example of how order can come from what seems like chaos at the quantum level.
Wow. This is already blowing my mind, and we're just getting started. One thing that jumped out at me in the research was how the cluster size affected their calculations. What's that all about? What does cluster size have to do with these invisible magnets in the quantum realm?
That's where it gets even more interesting. Basically, even in theoretical calculations, the size of your model matters. The cluster here refers to how much of the material the researchers considered in their calculations.
So it's like trying to understand the ocean by looking at a thimble full of water.
Exactly. You need a big enough sample to accurately capture what's happening. In their research, Heisenberg and Tomlinson found that to get a good read on the staggered magnetization, they had to consider a large enough chunk of the material.
It's like you need that bigger picture to grasp the true scale of what's going on. But why is that? Why do larger clusters give a more accurate picture of this staggered magnetization?
It all comes down to the fact that at the quantum level, things are always fluctuating, always in motion. And these tiny temporary deviations from the average spin, they can really complicate things.
Yeah.
Smaller clusters don't capture the full range of these fluctuations, so you get less accurate results. Larger clusters, on the other hand, they average out these fluctuations, giving us a much clearer understanding of the true magnetic order.
That's fascinating. It's like you have to zoom out to see the entire forest instead of getting lost in the details of individual trees. You get a much clearer picture of the overall pattern that way. This deep dive is already giving me a lot to think about, but why should I, as someone interested in the bigger picture, care about this whole concept of staggered magnetization? What's the so what here?
Think of it like this. It's about potential. Staggered magnetization and antiferromagnetism in general. It's like this untapped resource in the world of material science.
Untapped resource. Okay, now you've got my attention. Give me some examples. What kind of cool tech could come from understanding and using this staggered magnetization?
Well, imagine electronics that are way more energy efficient and way less likely to get interference. That's one of the big things antiferromagnetic materials offer. Because the spins are opposite, they don't create those stray magnetic fields that mess things up or waste energy.
That's huge. My phone battery would love a little of that antiferromagnetic magic.
Right. And we're not just talking smaller, faster gadgets. Antiferromagnets. They could lead to whole new ways of storing and processing information. Imagine computers that use the way electrons spin to actually represent data. Like it could mean way denser, way more powerful data storage.
So are we talking about completely changing how computers work? This isn't just like a little upgrade. This is like a whole new game, right?
Exactly. It's all about looking at the fundamental properties of matter and using them to create technologies we haven't even dreamed of. That's the beauty of this kind of research. It opens up possibilities we never even knew existed.
You know, hearing you talk about this perfect checkerboard pattern of spins, it makes me think of something I read about the Neal state. What exactly is that?
Yes, the Neal state. Named after Louis Neal, a physicist who did some groundbreaking work in magnetism. It describes that ideal arrangement of spins in an antiferromagnet, that perfect checkerboard you mentioned, where every single spin lines up perfectly opposite its neighbors.
So it's like the gold standard of staggered magnetization, as organized as it gets.
You got it. And in their research, Heisenberg and Tomlinson actually used that Neal state as a kind of reference point, assigning a staggered magnetization value of 1. It's like a benchmark to compare the level of order in actual materials. That 0.71 they calculated, it suggests a really high degree of order in that 2D Heisenberg antiferromagnet, adding even more weight to the idea of long-range antiferromagnetic order.
Okay, that makes total sense. So they're basically saying this material has about 71% of that perfect checkerboard order you see in the Neal state. But this research was done way back in 1994. What's happened since then? Has it led to any of those big discoveries or technologies yet?
That's a great question. But science, it's a marathon, not a sprint. While this research was a huge step forward, it can take years, decades even, for these kinds of discoveries to turn into technology we use every day. It's like planting a seed. You got to nurture it, be patient, and give it time to grow.
So what you're saying is the full impact of their research might not be known for years. It's like we're in the very first chapters of a scientific revolution, and we have no idea how it's going to end. It's pretty exciting.
It is exciting. And it's not just about waiting around. It's about continuing to push the limits of what we know. Every little discovery, every step forward brings us closer to unlocking the possibilities of these materials. Take spintronics, for example. That's one area where antiferromagnetism has a lot of people excited.
Spintronics. Okay, you're going to have to break that one down for me. That sounds straight out of Star Trek. Spintronics. Okay, you're going to have to break that one down for me. That sounds straight out of Star Trek.
It kind of is. Think of it this way. All of our electronics today, they use the charge of electrons to carry information, right? But spintronics, that's about using the spin of electrons as well. Remember how we were talking about that up-down pattern in antiferromagnets? That built-in spin arrangement makes them perfect for spintronics.
So instead of just ones and zeros, you could have all kinds of combinations, like maybe up down is a one and down up is a zero. It'd be like a whole new language for computers.
Exactly. It opens up this whole new dimension for writing and manipulating information. And here's the best part. Electron spins, they can be switched way faster than electron charges. That means spintronics could be so much faster than the electronics we use now.
Okay, I see where you're going with this. Faster, more efficient, a totally new way of processing information. It sounds like antiferromagnetism could be a real game changer. But if it's so promising, why aren't we seeing it everywhere? What's holding it back?
That's the million-dollar question. One of the biggest challenges is that those opposing spins in an antiferromagnet, they kind of cancel each other out. That makes them really hard to detect and even harder to control from the outside. They're like little ninjas. They don't create those strong magnetic fields we're used to seeing with regular magnets.
So it's like trying to lead an orchestra where everyone wants to play a different song at the same time.
Something like that. But even with all that, scientists are making some amazing progress. They're finding new ways to control and detect those electron spins in antiferromagnets, even without those strong magnetic fields,
Yeah.
which could pave the way for some really cool applications.
So we're really on the edge of a spintronic revolution, all because of these invisible magnets and their alternating spins. It's amazing to think this was all just theoretical physics a few decades ago, and now we're talking about changing the world with it.
It really shows you the power of basic research. People like Heisenberg and Tomlinson digging deep into the quantum world just to understand how these magnetic interactions work. They laid the foundation for all of this. And to think, it all started with something as seemingly simple as staggered magnetization.
This has been an amazing deep dive. We've gone from tiny invisible magnets to mind-blowing possibilities like high-temperature superconductivity and spintronics, all thanks to this research. I have to admit, I'm a little overwhelmed, but in a good way. What's the one big thing you want me to remember from all of this?
I think the biggest takeaway is that the world is full of surprises. Sometimes the most groundbreaking discoveries come from exploring the things that seem a little bit strange, a little bit out there. Who would have thought that the way electrons spin inside a material could be the key to revolutionizing electronics, computing, maybe even how we understand the universe? It reminds us to never stop being curious, never stop exploring.
Absolutely. You know, going through all of this, I couldn't stop thinking, if scientists can figure out staggered magnetization so precisely now, what else are they uncovering in the quantum world? What other amazing discoveries are right around the corner? These are exciting times to be talking about these topics, that's for sure.
I completely agree. This is just the beginning, and it's an incredible time to be a part of it all.
That's all the time we have for today's deep dive. A huge thank you to you, our listeners, for joining us on this journey of discovery. Make sure to check out the show notes for even more information and links to some fascinating resources. We'll see you next time for another deep dive into the world of science.